We're now ready to talk about the last topic in section 2.5 in the OpenStax Calculus book, volume 2. In this particular video, we're going to focus on hydrostatic pressure and hydrostatic force. This will be a relatively short video, and I only have 2 examples for you. This isn't something that we get to as often as we'd like to in our calculus classes, so hopefully your class makes it there as well. What we want to talk about here is hydrostatic force and hydrostatic pressure. So we looked at force and work in the last 2 videos. And in this one, what we want to think about is the force and pressure exerted on some kind of object that's actually under a liquid, in most cases, water. So some kind of object submerged in this liquid. Now, in the English system, again, remember that force is measured in pounds. And in the metric system, we have newtons. Now, pressure is force per unit area. So you take the force and you divide by the area. In the English system, then, we have pounds per square foot, or more commonly, pounds per square inch, which is also called PSI, pounds per square inch. In the metric system, we have newtons per square meter, which are called pascals. Named for Etienne Pascal, who is a well-known or maybe it's Blaise Pascal, both well-known mathematicians. What we want to consider first is a flat plate or a lamina, something very, very, very thin that has been submerged horizontally in water at a depth of S. Now, by horizontally, we mean that it's down there like this, all right? So it's not submerged like this. We'll look at something like that, but we're talking about this first. And the reason it's important is because then every point on the plate is at the same depth, all right? S is the same for all points on the plate. That would not be the case if we turned it this way. If it were vertical, this would have a different depth from this point down here. So we're thinking about these plates, and we have it oriented horizontally. Now, the force on the plate is going to be the weight of the water above it. So that's given by the force equal to A times rho times S. Now, A, of course, stands for the area of the flat plate. We're considering it to be roughly 2-dimensional. Rho is the weight density of water, which is 62.4 pounds per cubic foot. Right? And then S, of course, is the depth of the plate in the water. Let me share my screen with you so that you can see my notes more easily. Now what we want to look at and think about is the hydrostatic pressure. That's the pressure exerted by the water onto the submerged object. Now you can see that the object is down here at a depth of S. Now I like to draw my S so that it goes from the surface of the water down to whatever the object is that's submerged. That is not always the way it has to be set up. We'll do one where that is the case and one where it is not the case, so that you can see that S can actually be set up quite differently. All right. And then to find the pressure, you just take the force and you divide by the area of the plate. And that will give you the weight density of the water times the depth. Now what we want to do is think about what would happen if we were to rotate the plate. So we started with a plate that was oriented like this, and then we orient something like this. So if we're turning it from horizontal to vertical, the problem is that each point is at a different depth. Now, what are we going to do? Well, what do we always do? We're going to take it, we're going to divide it. So you can see all these little lines here. We're going to divide this plate into a bunch of little horizontal strips. And each little horizontal strip is going to be so narrow, so thin, that it's practically at the same depth. So we're going to assume that on each little strip, it's at the same depth, and that the force of the water onto that is the same. And so we're going to consider it to be constant on that little strip right there. And we're going to compute the force there on that little strip. And then we're going to add the forces on all the little strips together. Then we'll take the limit as the number of strips goes to infinity and the width of each strip goes to 0. and we'll get a definite integral. Sounds like something we might have done before. So we can't apply the formula for rho times the area times the depth directly because the depth is varying from point to point on that vertically oriented surface. So we have to divide it up. So typically what we do is we'll split it up so with a frame of reference, and this time I do what the book does. I orient it so that the x-axis is still vertical, but this time I make the downward direction positive. And I make the point x equals 0 be something logical. It could be the top of the surface of the water, or if it's the case of a dam, it might be the top of the dam where the water is actually a little below that. So those would be logical places to set the origin x equals 0 at. Now, S of x is going to be the depth at point x. Now, we often let x equals 0 correspond to the surface of the water. And so in many cases, S of x and x are actually the same thing, but not always. All right, we're going to do the more general case where S of x denotes the depth at point x, and we're going to derive the formula so that you can choose a different reference point for x equals 0 if it's more appropriate. So here's what we have with our plate. This one is round instead of mine, which was rectangular. And so what we've done is, because it's oriented vertically, it's very, very thin, practically two-dimensional. When we're looking at this, we're going to divide it into all these different little regions like this. So we're going to have little strips coming across like this. And on each little strip, we're going to say that the width of the strip is the delta x or dx. And you can see it marked here on the picture. This is our delta x. Now, because it is extremely flat, practically two-dimensional, all I really need to compute is the area of this particular strip. So the area of the strip is going to be given by the width of the strip, which is given by W of x star, times the length of the strip, or you can call it height times width, or whatever you want to call it. Basically, you're going to multiply this W times delta x, and that will give you the area of that orange strip. Now, where did x star come in? Because we're dividing this, we're partitioning the plate into little sub-partitions in different partitions. Somewhere we have an x sub I and an x sub I minus 1. And remember that the origin is up here. So x sub I minus 1 is going to be further up rather than the other way around. And what we do then is we say, well, I gotta pick some point in here to compute this width or length, whatever you want to call it, to compute this width at. So I'm just going to pick some arbitrary point that's between x sub I minus 1 and x sub I. So in each little one, I'm going to pick a spot and say, you get to be the width of this particular strip, this rectangle. And then as the widths go to 0, then the x becomes, the x sub I star gets closer and closer to the value of x as we take the limit as the number of partitions goes to infinity. So I also take the depth at that particular value, x sub I star. So for each one of these, I'm going to have an x sub I whatever star, and that's going to be the depth. And then I'm going to compute the area by taking the width at that particular point of the plate. How wide is the plate? And then I'm going to multiply by delta x. You'll also notice over here, the plate itself is extending from x equal a right here down to x equal b. So that is the I guess you'd call it height of the plate, all right? So in the water. So the less deep is at A and the deeper is down here at B. And again, remember that our axis is running down as positive. And so this is x equals 0 up here, and then x gets larger as you move down, right? And you can see that it's got an arrow here on the x-axis. Okay, so the next thing that we want to do, of course, is compute the force that is on each individual little strip, the little orange things. So the force on the ith strip is given by the weight density of water, rho, times the area of that little strip times the depth in the water of that strip. Now, the strips are incredibly thin, and so we take this point x sub I star, we find the width at that point, and we use that to multiply by delta x to get the area, and then we multiply by the depth at x sub I star. Now, as the width of those goes to 0, x sub I star becomes x. So we add all the forces together, the individual forces in all the different strips, and then, of course, we're going to take the limit as n goes to infinity, and we're going to get the following integral. So as we take the limit, rho, of course, is the weight density of the liquid, and most of ours are going to be water. And then we have this formula that gives us the width of that particular flat surface at that point times the depth at that point. All right, S of x times dx, where W of x and dx multiplied together give us the area of that strip. And we integrate from the depth of the top of the plate to the depth of the bottom of the plate. So from less deep to more deep. Now let's take a look at two examples. I have two examples for you here. And the first one, we have a water trough again. It's 15 feet long. And again, the ends are isosceles triangles like the one we did last video. And the base of the isosceles triangle is 8 feet and the height is 3 feet. We want to find the force of the water on the end of the trough if the trough is completely full of water. So this picture I don't think is as good as the last one I had, but at any rate, this is supposed to be the trough. I don't like that they've extended these lines further out, that they should have a break between the picture and the line. It looks a little weird. And the water is supposed to be going all the way to the top, so that's a little off as well. So, but again, the isosceles triangle is 8 feet at the base, and this depth here of the water is 3 feet. The depth of the tank itself is 3 feet, and the tank is 15 feet long, right? So obviously not to scale. So when we're looking at the end of this particular tank, we have this isosceles triangle. We have 8 feet here. We are setting our origin at the top of the tank. The water is supposed to go all the way to the top. So imagine that we've got blue all the way to the top. It's 3 feet deep. And I don't know where the 5 came. I thought it said 15. Let's go back and check. Yes, 15 feet long. So there's an error here. Oh, this is 5 feet. Okay, so I thought they were talking about the length of the trough. They're not. They're actually talking about this slanted side of the isosceles, how they get it. Well, if you take a perpendicular from an isosceles triangle, it bisects the side across from it, which tells us that this length right here has to be 4 feet. And this length over here has to be 4 feet. And then, of course, we have a right triangle. And because we have a right triangle, we can use the Pythagorean theorem. And then we know that 3 feet squared plus 4 feet squared gives us 25 square feet, which tells us the length of the hypotenuse is 5 feet. We probably, I don't think we'll need that, but we have it. Now we want to draw a strip in the water, and we want to label the width of it Wx, and we want to mention what the depth is. This time I set the depth at the level of the water. So the water actually extends to the top of the tank. So I should go ahead and fill in the rest of this water. That's not dark enough. The water actually goes up to the top. Bad picture. What can you do? All right, so we've got water up to the top of the tank. And so I set the origin right there at the top surface, and x extends down. That's the positive direction. So s is equal to x here in this case. Now, my particular surface here, my little flat plate. This is the end of the trough that we're worried about. This isn't a 3D thing, it's a flat thing. We're worried about the end of the trough. So I'm dividing the end of the trough into these little horizontal strips here. And the width of it goes all the way across, which is W of X. And you know what's coming. You can see it already. We need similar triangles. So we're going to have to use similar triangles to get an equation for W of X. Now, here's the similar triangles that I set up. I can't quite get it all on there. So first off, on this one, I use the isosceles triangles for similar triangles. They're also going to be similar. This angle here and this angle here have to be the same because you have two parallel lines cut by a transversal and corresponding angles are congruent. And so we know that that angle equals that angle. Now, what does that tell me? Well, if I set up the width of my strip over the width of the tank, which is 8 feet, then I should have the depth of my particular strip over the depth of the tank. The tank's depth is 3 feet. Now, the strip itself is at 3 feet minus X. So that would be this part of the triangle, all right? Not the location of the strip. So let me outline the two triangles that we're making into similar triangles for you. Here's the first one. That's for the entire tank. And this is the second one. Right? Notice that they do have corresponding angles here. They share the bottom angle. Therefore, all three angles are the same, so they must be similar. So we're allowed to set this up. This distance here is 3 feet minus X because this distance is X. So when we're looking at this right here, this distance is X. So this distance right here, oops. Well, wow, that really went far away. Okay. Where'd it go? Here we go. All right, I'll have to redraw it because it took it off. This distance here is 3 feet minus the X because X plus this has to be 3 feet. All right. So when I set up the proportion, I get the following. All right. I get that W of X over 8 feet has to be 3 feet minus X over 3 feet. When you cross multiply and work it out, you end up with W of X is 8 feet minus 8/3 of X. So we have a relationship between X and W of X, and our S is the same as X. So now we can compute the force on the end of the trough. So again, it's a flat two-dimensional surface. It's just the surface of the end of the trough. So we're going to take the density, weight density of water. Here is rho. This is not density anymore. It's weight density, which is 62.4 pounds per cubic foot, times the width function for our particular strip, which is 8 feet minus 8x over 3, times our S of X, which turned out to be the same as X. That's where I set it. And so I have X there. You can distribute, pull out the constant 62.4 pounds per cubic foot. And when you integrate, you end up with 748.8 pounds. Now remember that pounds is a measure of force. So now we have the force on that particular thing. Now, how would you get the hydrostatic pressure? Well, if you want the hydrostatic pressure, then you need to come back to your figure and you need to compute the area of the region that you're talking about. And in this case, the area of my triangle has a base of 8 feet and a height of 3 feet. So 1/2 the base times the height, half of 8 would be 4 feet, times the height would be 3 feet. And so the area would be 12 square feet. So then I could take this pressure that this force that I got here, and to compute the pressure, not rho, notice this has a straight stick, not rounded, straight stick, this is a P, not a rho. So P for pressure is going to be given by the force divided by the area. So in our case, 748.8 pounds. And it is, what did we say, 12 square feet on the end. So whatever that comes out to be, that's the amount of hydrostatic pressure on the end of that particular trough. And I got 62.4 pounds per square foot, right? Which is quite a bit of force, right? So it's a lot of pressure on there, right? Now we want to look at one more example. This is the Hoover Dam. So when we're looking at the Hoover Dam, the shape of it, it is a little bit curved, but we're going to ignore the three-dimensional curve to it. We would need, again, calculus 3 to be able to handle that. So we're going to instead assume that it's flat. It is roughly flat, but it does have a little bit of a bend to it, and we're ignoring that. It's shaped like an isosceles trapezoid. So isosceles means that this angle and this angle are equal to each other, and these two sides are equal to each other as well. And the top upper base is 1,250 feet. The bottom base is 750 feet. It's 750 feet tall. It's a massive amount of concrete. So when the reservoir is full, the lake at the top, the maximum depth is about 530 feet. So the depth of the water comes up to about here. With the top 10 feet, the water level is about 10 feet below the top of the dam, right? So it doesn't come all the way up to the top, which is probably good. You don't want it spilling over, all right? We want to find the force of the water on the face of the dam, right? And then we'll talk a little bit about how to find the hydrostatic pressure as well. So we're going to choose a frame of reference. This time, we are not going to choose X and S to be the same. Now, you could, but you don't have to. So in this particular case, what I did was I chose the top of the dam to be X equals 0. So I'm putting my origin right here. All right, so there's the origin. All right, and this is my X-axis, which is going down. All right, so I've got 1, 2, 3 coming down like this. Now I put the surface of the water to be S equal to 0. So the water then is actually X minus 10 because the water level is 10 feet below the top of the dam. So I put X to be the distance from the top of the dam, and I put S to be the depth of the water, which is going to be X minus 10, right? So the next thing we're going to do is we're going to have to use similar triangles again. This is a very common thing to need to do to get a width function. Now, again, what we're doing is we're dividing the end of the Hoover Dam into tiny little strips. My hand's not too steady. It's a little late. And so we're looking at each one of these, and each one of these has a height or whatever of dx. And the width is going to be basically this length of it. So we can call this W sub I. And it depends on the depth because it is a trapezoidal shape. So the lower it goes, the narrower it gets. So we need to figure out some kind of relationship between the width and the X value, the distance below the top of the dam. So here's a picture where the different sides are measured again. Remember, the top is 1,250 feet. The bottom is 750 feet. So we put vertical lines perpendicular to the base coming up here, which basically makes this interior region, well, it makes it a square. All right, and that gives us two right triangles on either side, and they're the same because it's an isosceles trapezoid. So this is going to be 250 feet because after I take the 750 and subtract from 1,250, I get 500, and they're symmetric. So this is 250 and this is 250. Not all trapezoids are symmetric, but if it's isosceles, it is. All right, now this gives us a triangle coming down like this. And again, I've got my little strip in here. So here's my little strip coming all the way across. And I want to know what W of X is. Well, I know what the center part is. The center part right here is 750 feet. I mean, that's because it's square, so I can tell. But I don't know what this is over here, and I don't know what this is, but I know they're the same because it's symmetric. So I want to find this distance right here, which your book is labeled R. I probably would have called it something different, but R works for me. So when we're looking at this, we again have similar triangles. So let me outline the two similar triangles for you. So we've got right angles there and there, and the large triangle is here, and the smaller triangle is here. Right? Now you can tell that they both have a right angle in them, and they both share the angle at the bottom. If two of the three are the same, then all three are the same. Also, this is two parallel lines cut by a transversal, and corresponding angles are equal. I know you thought you'd never use that, but it's being used right here. So these are similar triangles, so I can set up a proportion. So now down below, you can see that I set up the proportion. So I have R, which is this horizontal measure, over 250 feet, which is this horizontal measure, equal to, and now I need the depth here from the top of the dam, not the depth of the water, but the depth from the top of the dam. Now I know that this right here is at X, but the triangle I'm looking at is down here. So this distance down here is the total depth, 750 feet, minus the X, so 750 minus X. So then I set it up with 750 feet minus X over 750 feet. I solve it for R, and I get that R is 250 feet minus X over 3. But remember that we've got two of these. We've got one on either side. So over here on this side, we have another R. So what we actually need is 2R. So we're going to take the width, which is the 750 coming from the center part. This part right here is 750 feet, plus R from the left and R from the right, which is 2R. And that ends up giving us 1,250 feet minus 2X over 3, which is a relationship based on X. So now that we know what the width is, we can set up our integral. Now we want to figure out the force caused by the water. So we need to figure out, well, where is the water and what are we looking at? So we're going from 10 to 540. Now why 10 to 540? X was set at the top of the dam. So the water starts 10 feet below that at 10. So again, we're going where the water is, and the water is 530 feet deep. But it starts at 10, so 530 plus 10 gives me 540. This is the weight density of water, 62.4 pounds per cubic foot. That's rho. Here's my expression for the width of each strip. And then I need to multiply by the depth of the water. So this is from the surface coming down. So this is X minus 10, because the surface of the water is 10 feet below where X starts. And then, of course, you just multiply it out, then integrate, do a little work. You may want to pause the video so that you can get all of this written down. And you end up with this massive, massive amount of force. You end up with 8,832,245,000 pounds of force on the dam. It's a massive amount. You can write it in tons. Remember, a ton is 2,000 pounds. It is still 4.4 million tons of force on the dam. Now, the last thing we might want to talk about is the hydrostatic pressure. Now, in order to figure out the hydrostatic pressure, we simply take the force that we got previously and we divide by the area of the dam. Now, the area of a trapezoid is the average of the two bases, the top and the bottom, multiplied by the height. So ours was 750 feet at the base, 1250 at the top, had a height of 750. And if you compute the area of the surface of the Hoover Dam, you get 750,000 square feet. And when you divide, you still end up with almost 5.9 tons of pressure per cubic foot. That is massive. That is just unbelievable. Now you might argue, well, but the water's not touching all parts of this part of the dam. So you might want to use some trigonometry and geometry to restrict it to just the part where the water is. But the way that dams are built, it distributes the force over the entire face of the dam. And so this is actually a good way of measuring how much force is on the face of the dam. I hope that this makes sense to you and that you've enjoyed learning a little bit about hydrostatic force and hydrostatic pressure. And I hope that you will join me for the last video out of this chapter of our textbook, which will be focusing on centroids, centers of mass, and centers of gravity. I hope to see you there.